Okay, let's find the interest earned on $5,000 that gets invested at 3% compounded monthly for 10 years. Ooh, okay. Uh, if you put money into certain ways of earning more money on it, like lend it to the bank in a bond or in some kind of a trust fund, it can pay you back money. That's called interest. So in this case, I have $5,000. I give it to the bank. They say, look, we'll give you 3% a year, but every month we'll figure out how much we owe you and compound that, and we'll do that for 10 years. And this question is, how much money do they have to give me back at the end? So obviously they have to give me my $5,000 back, but then they have to give me more for borrowing my money. And it turns out that there's a formula for this, which is A equals P times 1 plus R over N to the NT. And although this looks kind of complicated, it's actually not too bad. This is the total amount that they owe you back. This is what's called the principal. Principal is how much money did you originally give them, so $5,000. This R here is the interest rate per year, so that's the annual rate, and N is the number of compounding periods per year, so that's the same as this N up here, and T is the number of years. Okay, so the total amount that they owe me back is, well, I gave them $5,000, and it was at 3% every month, and there's 12 months in a year, and there are 12 months in a year times 10 years. So the total amount of money that they need to give me back is 5,000, and I'm just going to calculate what this number is inside here. And I got 1.0025, so that's my base. And remember, the base has to be positive, like bigger than 0. It can't be equal to 1, so this is just a little bit bigger than 1. And so I've got this kind of a function going on, which is an exponential function. I've got a little tiny bit of an increase a lot of times, 120 times, 10 years, 12 months each year, compounded monthly. So 120 times of a little tiny bit of an increase. And if I calculate what this is worth, I get a grand total of $6,746.77. So this formula gives me the total amount of money that they owe me back. But I gave them 5,000, so the 5,000 that they give me back was what they were going to give me back just for lending it to them, obviously. The other money, which is $1,746.77, that's the interest that I earned. The other $5,000 I didn't earn, that's what I gave them. So the extra money that they give me back for lending them this money is almost $2,000, which isn't too bad. You know, if you have some spare money, lending it to a bank is a pretty good way to make some money back. Of course, you have to wait 10 years or so to get $2,000, but yeah, it's a way of investing your money to make some money back later on. Let's take a look at another example of where we find exponents in real life. Okay, so in other areas in archaeology or in chemistry with half-lives, so you might even think about this as physics as well. The half-life of carbon-14 is about 5,700 years. So what that means, half-life is if you have a certain amount of carbon-14, half of it will disappear, radioactively disappear, in about 5,500 years. So if you have, say, a sample of 270 grams of this carbon-14, it will disappear every 5,000 and a bit years. Half of it will disappear. How much would you have in 40,000 years from now? So again, there's a formula for this, and it looks something like this. The total amount that you'll have equals the starting amount, or initial amount, times 1/2, because we're dealing with half-life. So I'm multiplying 270 by a half, and then I'm multiplying it by a half again and a half again. That's why it's a half raised to some exponent. Notice that the base is a half here because it's going multiplying by half, like dividing by 2 each time, whereas in the last time it was increasing by a little tiny bit each time. So you can see by the base whether or not you're dealing with a graph that will look like a half-life graph, which goes down and down and down and down, or a graph that looks like a money exponential graph that goes up and up and up and up. And then there's a couple different things on the top. There's the time, which is the total time that you are dealing with. In this case, that's 40,000 years. And then there's the half-life time. So if we plug these things in, the initial amount that I had was 270 grams, and it's halving. And how many times is it halving? Well, it halves whatever number of times I get if I take 40,000 and divide it by 5,700. So cranking all this through a calculator, I get an answer that's approximately equal to 2.08 grams. So there's not that much carbon left over. Well, a couple grams of carbon is not insignificant. And this is actually how scientists, archaeologists can do carbon dating. If they work backwards with this and say, oh, I've got this sample of 2.08 grams, how much was there in this entire animal or being or whatever it happened to be? And they can work out how old it was that they're looking back in time. So how long has this mummy or artifact been buried? And it's a pretty interesting way that scientists can go back in time to estimate how old things are, especially for archaeology. Okay, we'll see you in class.